And now we're going to problem number 4. Now we have a capacitor with a dielectric. And that is always a little bit harder. Here is the capacitor. The area is 1 square meter. It has a distance d between the plates. And what we are being told is that the net E field in the capacitor is 1.4 times 10 to the 6 newtons per coulomb or volts per meter, whichever you prefer. And there is here a dielectric inside with a dielectric constant of 4.5. We're being asked what the free surface charge density is on the plates, that we call that per definition free, and what the induced surface charge density is on the dielectric. And for that I'm going to make an enlarged picture. Here, the top plate, I make artificially a gap, but the gap is not there. Here is the dielectric, and again I make here artificially a gap. Let's assume that the top plate is positively charged. Then there will be free charge here on this plate. Let's call it sigma free. And there will be an equal amount of negative charge, again, sigma free. In the absence of a dielectric, there would be an electric field. I call that the E free. And that free field is easily calculable. That would be sigma free divided by epsilon 0 in the absence of this dielectric. However, the dielectric is going to be charged itself. We get negative induced charge here. I call that sigma induced. It has the opposite sign. And we get positive induced charge here, sigma induced positive. And this positive and this negative charge will produce an electric field, I call it E induced, which is opposing the electric field without the dielectric. And what you have in here is, of course, the net electric field, E net, which is the vectorial sum of E free plus E induced. All right, let's now apply Gauss's law to a little pillbox, like so. With an area E here, the electric field outside the plane capacitor equals 0. Inside here I have an electric field, which is this net field. It's pointing perpendicular to this surface. There is no flux leaking out through the sides. And I want to write down now Gauss's law in 2 different ways. First, I'm going to say that E net times that area A is the total charge inside that box divided by epsilon 0. What is the total charge inside that box? That is sigma free minus sigma induced. The minus sign because the induced charge here is negative, and I have assumed that this metal plate here is positive. Times A, this is the total charge inside my pillbox, divided by epsilon 0. But, and this is the definition for dielectric, it is also equal to sigma free times A divided by that dielectric constant K epsilon 0. This is all the same. And if you never want to bother with induced charges, you can just forget about this and immediately write down the K here. And what you see here, that the effect of the dielectric is, if the dielectric constant is 4.5, that the E field, because of the dielectric, is 4.5 times smaller than what it would have been if the dielectric hadn't been there. You can just see this. If the dielectric hadn't been there, this would have been the answer. That would have been the E free. That is this field. But since the dielectric is there, that's not the case. Now, we lose the A's. And now it's a little bit up to you. Let us combine first this one with this one. I have one equation with sigma free as with sigma, no, I'm going to do it slightly differently. I first take this, and that gives me one equation with sigma free as unknown. So you solve immediately for sigma free. Now I take this equation, but I know sigma free, and so this equation now is again one equation with sigma induced as unknown. So now you can solve for sigma induced. If you want to combine them in a clever way, if you like that, it's easy to prove that sigma free equals 1 minus 1 over k times sigma induced. Don't try to remember that, but that's what will follow from these results. So due to the dielectric, the net electric field is reduced. And so if I summarize the situation, the E field, this is my shorthand notation, because of the dielectric, is 4.5 times lower than what it would have been if the dielectric hadn't been here. Therefore, the potential difference over the plates is 4.5 times lower, because remember, the potential difference is simply E times D, and D is not changing. C equals Q free divided by the potential difference. Q free is not changing, the potential difference goes down, and so the capacitance goes up by a factor K. So with the dielectric, the capacitance has a 4.5 times larger capacitance. The little u, which is energy density, how many joules per cubic meter, equals 1/2 times the dielectric constant times epsilon 0 times E squared. This would be in joules per cubic meter. It's easy to calculate how much this is. I found it to be 39.0 because I think you know E, you know K, so that is rather easy. Since you know, if you want to know the total U, you have to take the little u times the volume, and that is the little u times the area A times the separation D. This was 1 meter. You are given D, so you can calculate what the total electric energy is in this system.